Hi everyone, and welcome back to 6S191. Today's a really exciting day because we'll learn about how we can marry the very long-standing field of reinforcement learning with a lot of the very recent advancements that we've been seeing so far in this class in deep learning, and how we can combine these two fields to build some really extraordinary applications and really agents that can outperform or achieve superhuman performance. Now, I think this field is particularly amazing because it moves away from this paradigm that we've been really constrained to so far in this class. So far, deep learning, the way we've seen it, has been really confined to fixed data sets, the way we kind of either collect or can obtain online, for example. In reinforcement learning, though, deep learning is placed in some environment and is actually able to explore and interact with that environment, and it's able to learn how to best accomplish its goal. Usually it does this without any human supervision or guidance, which makes it extremely powerful and very flexible as well. This has huge obvious impact in fields like robotics, self-driving cars, and robot manipulation, but it also has really revolutionized the world of gameplay and strategic planning. And it's this really connection between the real world and deep learning, the virtual world, that makes this particularly exciting to me. And I hope this video that I'm going to show you next really conveys that as well.
StarCraft has imperfect information and is played in real time. It also requires long-term planning and the ability to choose what action to take from millions and millions of possibilities.
I'm hoping for a 5-0, not to lose any games, but I think the realistic goal would be 4-1 in my favor.
I think he looks more confident than TLO. TLO was quite nervous before. The room was much more tense this time. Really didn't know what to expect.
He's been playing StarCraft pretty much since he's 5.
I wasn't expecting the AI to be that good. Everything that he did was proper, it was calculated and it was done well. I thought I'm learning something. Yes! Yes! It's much better than I expected it to be. I would consider myself a good player, right? But I lost every single one of 5 games.
We're way ahead of what.
All right, so in fact, this is an example of how deep learning was used to compete against humans, professionally trained game players, and was actually trained to not only compete against them, but it was able to achieve remarkably superhuman performance, beating this professional StarCraft player 5-0. So let's start by taking a step back and really seeing how reinforcement learning fits within respect to all of the other types of learning problems that we have seen so far in this class. So the first piece and the most comprehensive piece of learning problems that we have been exploring so far in this class has been that of supervised learning problems. So this was kind of what we talked about in the first, second, and third lectures. And in this domain, we're basically given a bunch of data, X, and we try to learn a neural network to predict its label, Y. So this goal is to learn this functional mapping from X to Y. And I like to describe this very intuitively. If I give you a picture of this apple, for example, I want to train a neural network to determine and tell me that this thing is an apple. Okay. The next class of algorithms that we actually learned about in the last lecture was unsupervised learning. So in this case, we were only given data with no labels. So a bunch of images, for example, of apples, and we were forced to learn a neural network or learn a model that represented this underlying structure in the data set. So again, in the apple scenario, we tried to learn a model that says back to us, if we show it these two pictures of apples, that these things are basically like each other. We don't know that they're apples because we were never given any labels that explicitly tell the model that this thing is an apple, but we can tell that, oh, this thing is pretty close to this other thing that it's also seen, and it can pick out those underlying structure between the two to identify that. Now, in the last part, in RL, in reinforcement learning, which is what today's lecture is going to be focused on, we're given only data in the form of what we call state-action pairs. Now, states are what are the observations of the system, And the actions are the behaviors that that system takes, or that agent takes, when it sees those states. Now, the goal of RL is very different than the goal of supervised learning and the goal of unsupervised learning. The goal of RL is to maximize the reward, or the future reward, of that agent in that environment over many time steps. So again, going back to the apple example, what the analog would be that the agent should learn that it should eat this thing because it knows that it will keep you alive, it will make you healthier, and you need food to survive. Again, like the unsupervised case, it doesn't know that this thing is an apple. It doesn't even recognize exactly what it is. All it knows is that in the past it must have eaten it, and it was able to survive longer. And because it was a piece of food, it was able to become healthier, for example. And through these state-action pairs and somewhat trial and error, it was able to learn these representations and learn these plans. So our focus today will be explicitly on this third class of learning problems and reinforcement learning. So to do that, I think it's really important, before we start diving into the details and the nitty-gritty technical details, I think it's really important for us to build up some key vocabulary that is very important in reinforcement learning, and it's going to be really essential for us to build up on each of these points later on in the lecture. Now, this is a very important part of the lecture, so I really want to go slowly through this section so that the rest of the lecture is going to make as much sense as possible. So let's start with the central part, the core of your reinforcement learning algorithm, and that is your agent. Now, the agent is something that can take actions in the environment. That could be things like a drone making a delivery in the world. It could be Super Mario navigating a video game. The algorithm in reinforcement learning is your agent. And you could say in real life, the agent is each of you. Okay? The next piece is the environment. The environment is simply the world in which the agent lives. It's the place where the agent exists and operates and conducts all of these actions. And that's exactly the connection between the two of them. The agent can send commands to the environment in forms of actions. Now, capital A, or lowercase a of t, is the action at time t that the agent takes in this environment. We can denote capital A as the action space. This is the set of all possible actions that an agent can make. Now, I do want to say this, even though I think it is somewhat self-explanatory. An action is, or the list by which an action can be chosen, the set of all possible actions that an agent can make in the environment can be either discrete, or it can be from a set of actions. In this case, we can see the actions are forwards, right, backwards, or left. Or it could also be continuous actions. For example, the exact location in the environment, as a real number coordinate, for example, like the GPS coordinates, where this agent wants to move. Right, so it could be discrete as a categorical or a discrete probability distribution, or it could be continuous in either of these cases. Observations are how the environment interacts back with the agent. It's how the agent can observe where in the environment it is and how its actions affected its own state in the environment. And that leads me very nicely into this next point. The state is actually a concrete and immediate situation in which the agent finds itself. So for example, a state could be something like an image feed that you see through your eyes. This is the state of the world as you observe it. A reward now is also a way of feedback from the environment to the agent. And it's a way that the environment can provide a way of feedback to measure the success or failure of an agent's actions. So for example, in a video game, when Mario touches a coin, he wins points. And from a given state, an agent will send out outputs in the form of actions to the environment, and the environment will respond with the agent's new state, the next state that it can achieve, which resulted on acting on that previous state, as well as any rewards that may be collected or penalized by reaching that state. Now, it's important to note here that rewards can be either immediate or delayed. You should think of rewards as effectively evaluating that agent's actions, but you may not actually get a reward until very late in life. So for example, you might take many different actions, and then be rewarded a long time into the future. That's called the very delayed reward, but it is a reward nonetheless. We can also look at what's called the total reward, which is just the sum of all rewards that an agent gets or collects after a certain time t. So R of I is the reward at time I, and capital R of t is just the return, the total reward from time t all the way into the future, so until time infinity. And that can actually be written out, expanded. We can expand out that summation from R of t plus R of t plus 1 all the way on into the future. So it's adding up all of those rewards that the agent collects from this point on into the future. However, often it's very common to consider not just the summed return, the total return as a straight up summation, but actually instead what we call the discounted sum of rewards. Now, this discounting factor, which is represented here by gamma, is multiplied by the future rewards that are discovered by the agent in order to dampen those rewards' effect on the agent's choice of action. Now, why would we want to do this? So this is actually, this formulation was created by design to make future rewards less important than immediate rewards. In other words, it enforces a kind of short-term learning in the agent. A concrete example of this would be if I offered to give you $5 today or $5 in 5 years from today. Which would you take? Even though it's both $5, your reward would be the same, but you would prefer to have that $5 today, just because you prefer short-term rewards over long-term rewards. And again, like before, we can expand the summation out, now with this discount factor, which has to be typically between 0 and 1. And the discount factor is multiplied by these future rewards as discovered by the agent. And like I said, it is reinforcing this concept that we want to prioritize these short-term rewards more than very long-term rewards in the future. Now, finally, there's a very, very important function in RL that's going to kind of start to put a lot of these pieces together, and that's called the Q function. And now let's look at actually how this Q function is defined, remembering the definition of this total discounted reward, capital R of t. So remember, the total reward, R of t, measures the discounted sum of rewards obtained since time t. So now the Q function is very related to that. The Q function is a function that takes as input the current state that the agent is in and the action that the agent takes in that state. And then it returns the expected total future reward that the agent can receive after that point. So think of this as if an agent finds itself in some state in the world and it takes some action, what is the expected return that it can receive after that point? That is what the Q function tells us. Let's suppose I give you this magical Q function. This is actually, it really is a magical function because it tells us a lot about the problem. If I give you this function, an oracle that you can plug in any state and action pair, and it will tell you this expected return from time point t, from your current time point. I give you that function. The question is, can you determine, given the state that you're currently in, can you determine what is the best action to take? You can perform any queries on this function. And the way you can simply do this is that you ultimately, in your mind, you want to select the best action to take in your current state. But what is the best action to take? Well, it's simply the action that results in the highest expected total return. So what you can do is simply choose a policy that maximizes this future reward or this future return. Well, that can be simply written by finding the argmax of your Q function over all possible actions that you can take at the state. So simply, if I give you this Q function and a state that you're in, you can feed in your state with every single action and evaluate what the Q function would tell you the expected total reward would be given that state action pair, and you pick the action that gives you the highest Q value. That's the best action to take in this current state. So you can build up this policy, which here we're calling pi of s. to infer this best action to take. So think of your policy now as another function that takes as input your state, and it tells you the action that you should execute in this state. So the strategy, given a Q function, to compute your policy is simply from this argmax formulation. Find the action that maximizes your Q function. Now, in this lecture, we're going to focus on basically these two classes of reinforcement learning algorithms into two categories. One of which will actually try to learn this Q function, Q of S, your state and your action. And the other one will be called what are called policy learning algorithms, because they try to directly learn the policy instead of using a Q function to infer your policy. Now we're going to, in policy learning, directly infer your policy, pi of S, that governs what actions you should take. And this is a much more direct way of thinking about the problem. But first thing we're going to do is focus on the value learning problem and how we can do what is called Q learning. And then we'll build up to policy learning after that. Let's start by digging a bit deeper into this Q function. So first I'll introduce this game of Atari Breakout on the left. For those of you who haven't seen it, I'll give a brief introduction into how the game works. Now, the Q value tells us exactly what the total expected return that we can expect to see on any state in this game. And this is an example of one state. So in this game, the agent is this paddle on the bottom of the board. It's this red paddle. It can move left or right, and those are its two actions. It can also stay constant in the same place, so it has three actions. In the environment, there's also this ball, which is traveling, in this case, down towards the bottom of the board, and is about to hit and ricochet off of this paddle. Now, the objective, the goal of this game is actually to move the paddle back and forth and hit the ball at the best time, such that you can bounce it off and hit and break out all of these colored blocks at the top of the board. Each time the ball touches one of these colored blocks, it's able to break them out, hence the name of the game, Breakout. And the goal is to knock off as many of these as possible. Each time the ball touches one, it's gone, and you got to keep moving around, hitting the ball until you knock off all of the blocks. Now, the Q function tells us actually what is the expected total return that we can expect in a given state action pair. And the point I'd like to make here is that it can sometimes be very challenging to understand or intuitively guess what is the Q value for a given state action pair. So even if, let's say, I give you these two state action pairs, option A and option B, and I ask you which one out of these two pairs do you think has a higher Q value? On option A, we can see the ball is already traveling towards the paddle, and the paddle is choosing to stay in the same place. It's probably going to hit the ball, and it'll bounce back up and break some blocks. On the second option, we can see the ball coming in at an angle, and the paddle moving towards the right to hit that ball. And I ask you, which of these two options, state action pairs, do you believe will return the higher expected total reward? Before I give you the answer, I want to tell you a bit about what these two policies actually look like when they play the game, instead of just seeing this single state action pair. So let's take a look first at option A. So option A is this relatively conservative option that doesn't move when the ball is traveling right towards it. And what you can see is that as it plays the game, it actually does pretty well. It starts to hit off a lot of the breakout pieces towards the center of the game. And it actually does pretty well. It breaks out a lot of the colored blocks in this game. But let's take a look also at option B. Option B actually does something really interesting. It really likes to hit the ball at the corner of the paddle. It does this just so the ball can ricochet off at an extreme angle and break off colors in the corner of the screen. Now, this is actually, it does this to the extreme actually, because even in the case where the ball is coming right towards it, it will move out of the way just so it can come in and hit it at these extreme ricocheting angles. So let's take a look at how option B performs when it plays the game. And you can see it's really targeting the side of the paddle and hitting off a lot of those colored blocks. And why? Because now you can see once it braked out the corner, the two edges of the screen, it was able to knock off a ton of blocks in the game because it was able to basically get stuck in that top region. Let's take another look at this. So once it gets stuck in that top region, it doesn't have to worry about making any actions anymore because it's just accumulating a ton of rewards right now. And this is a very great policy to learn because it's able to beat the game much, much faster than option A and with much less effort as well. So the answer to the question, which state action pair has a higher Q value, in this case is option B. But that's a relatively unintuitive option, at least for me when I first saw this problem, because I would have expected that playing things, not moving out of the way of the ball when it's coming right towards you would be a better action. But this agent actually has learned to move away from the ball just so it can come back and hit it and really attack at extreme angles. That's a very interesting observation that this agent has made through learning. Now the question is, how can we use, because Q values are so difficult to actually define, it's hard for humans to define them, as we saw in the previous example. Instead of having humans define that Q value function, how can we use deep neural networks to model this function and learn it instead? So in this case, the Q value is this function that takes as input the state and action. So one thing we could do is have a deep neural network that gets inputs of both its state and the desired action that it's considering to make in that state. Then the network would be trained to predict the Q value for that given state action pair. That's just a single number. The problem with this is that it can be rather inefficient to actually run forward in time because remember how we compute the policy for this model. If we want to predict what is the optimal action that it should take in this given state, we need to evaluate this deep Q network n times, where n is the number of possible actions that it can make in this time step. This means that we basically have to run this network many times for each time step, just to compute what is the optimal action. And this can be rather inefficient. Instead, what we can do, which is very equivalent to this idea, but just formulated slightly differently, is that it's often much more convenient to output all of the Q values at once. So you input the state here and you output basically a vector of Q values. Instead of one Q value, now it's a vector of Q values that it would expect to see for each of these states. So the Q value for for each of these actions. So the Q value for action 1, the Q value for action 2, all the way up to your final action. So for each of these actions, and given the state that you're currently in, this output of the network tells you what is the optimal set of actions, or what is the breakdown of the Q values given these different actions that could be taken. Now, how can we actually train this version of the deep Q network? We know that we wanted to output these, what are called Q values, but it's not actually clear how we can train it. And to do this, this is actually challenging. You can think of it conceptually as because we don't have a data set of Q values, right? All we have are observations, state, action, and reward triplets. So to do this and to train this type of deep Q network, we have to think about what is the best case scenario? How would the agent perform optimally or perform ideally? What would happen if it takes all the best actions, like we can see here? Well, this would mean that the target return would be maximized. And what we can do in this case is we can actually use this exact target return to serve as our ground truth, our data set in some sense, in order to actually train this agent, to train this deep Q network. Now, what that looks like is first, we'll formulate our expected return if we were to take all of the best actions, the initial reward, R, plus the action that we select that maximizes the expected return for the next future state. And then we apply that discounting factor gamma. So this is our target. This is our Q value that we're going to try and optimize towards. It's like what we're trying to match, right? That's what we want our prediction to match. But now we should ask ourselves, what does our network predict? Well, our network is predicting, like we can see in this network, the network is predicting the Q value for a given state action pair. Well, we can use these two pieces of information, both our predicted Q value and our target Q value, to train and create this, what we call Q loss. This is essentially a mean squared error formulation between our target and our predicted Q values. And we can use that to train this deep Q network. So, in summary, let's walk through this whole process end-to-end of deep Q learning. Our deep neural network sees as input a state, and the state gets fed through the network, and we try to output the Q value for each of the 3 possible actions. Here, there are 3 different ways that the network can play. It can either move to the left, move to the right, or it can stay constant in the same place. Now, in order to infer the optimal policy, it has to look at each of these Q values. So in this case, moving to the left, because it sees that the ball is moving to the left, it sees that, okay, if I step a little bit to the left, I have a higher chance of probably hitting that ball and continuing the game. So my Q value for my expected total return, my Q value for moving left is 20. On the other hand, if I stay in the same place, let's say I have a Q value of 3, and if I move to the right out of the way of the ball, in this case, because the ball is already moving towards me, I have a Q value of 0. So these are all my Q values for all of the different possible actions. How do I compute the optimal policy? Well, as we saw before, the optimal policy is obtained by looking at the maximum Q value and picking the action that maximizes our Q value. So in this case, we can see that the maximum Q value is attained when we move to the left with action 1. So we select action 1, we feed this back into the game engine, we send this back to the environment, and we receive our next state. And this process repeats all over again. The next state is fed through the deep neural network, and we obtain a list of Q values for each of the possible actions, and it repeats again. Now, DeepMind showed that these networks, deep Q networks, could be applied to solve a variety of different types of Atari games, not just Breakout, but many other games as well. And basically, all they needed to do was provide the state pictorially as an input, passing them through these convolutional layers followed by nonlinearities and pooling operations, like we learned in lecture 3. And on the right-hand side, it's predicting these Q values for each possible action that it could take. And it's exactly as we saw in the previous couple of slides. So it picks an optimal action to execute on the next time step, depending on the maximum Q value that could be attained, and it sends this back to the environment to execute and receive its next state. This is actually remarkably simple because despite its remarkable simplicity, in my opinion, of essentially trial and error, they tested this on many, many games in Atari and showed that for over 50% of the games, they were able to surpass human-level performance with this technique. And other games, which you can see on the right-hand side of this plot, were more challenging, but still, again, given how simple this technique is and how clean it is, it really is amazing that this works at all to me. So, despite all of the advantages of this approach, the simplicity, the cleanness, and how elegant the solution is, I think it's, and I mean, above all that, the ability for this solution to learn superhuman policies that can beat humans, even on some relatively simple tasks, there are some very important downsides to Q learning. So the first of which is the simplistic model that we learned about today. This model can only handle action spaces which are discrete, and it can only really handle them when the action space is small. So when we're only given a few possible actions as each step. It cannot handle continuous action spaces. So for example, if an autonomous vehicle wants to predict where to go in the world, instead of predicting to go left, right, or go straight, these are discrete categories. How can we use reinforcement learning to learn a continuous steering wheel angle? One that's not discretized into bins, but can take any real number within some bound of where the steering wheel angle can execute. This is a continuous variable. It has an infinite space, and it would not be possible in the version of Q learning that we presented here in this lecture. It's also, its flexibility of Q learning is also somewhat limited because it's not able to learn policies that can be stochastic, that can change according to some unseen probability distribution. So they're deterministically computed from the Q function through this maximum formulation. It always is going to pick the maximum, the action that maximally elevates your expected return. So it can't really learn from these stochastic policies. On the other hand, to address these, we're really going to dive into this next phase of today's lecture focused on policy gradient methods, which will hopefully, we'll see, tackle these remaining issues. So let's dive in. The key difference now between what we've seen in the first part of the lecture and the second part that we're going to see is that in value learning, we tried to have a neural network to learn our Q value, Q of our state given our action. And then we use this Q value to infer the best action to take given a state that we're in. That's our policy. Now, policy learning is a bit different. It tries to now directly learn the policy using our neural network. So it inputs the state and it tries to directly learn the policy that will tell us which action we should take. This is a lot simpler since this means we now get directly the action for free by simply sampling straight away from this policy function that we can learn. So now let's dive into the details of how policy learning works. And first, I want to really drive in this difference from Q learning, because it is a subtle difference, but it's a very, very important difference. So deep Q networks aim to approximate this Q function again by first predicting, given a state, the Q value for each possible action. And then it simply picks the best action, where best here is described by which action gives you the maximum Q value, the maximum expected return, and execute that action. Now, policy learning, the key idea of policy learning is to, instead of predicting the Q values, we're going to directly optimize the policy, pi of s. So this is the policy distribution directly governing how we should act given a current state that we find ourselves in. So the output here is for us to give us the desired action in a much more direct way. The outputs represent a probability that the action that we're going to sample or select should be the correct action that we should take at this step. Right? In other words, it will be the one that gives us the maximum reward. So take, for example, this. If we see that we predict these probabilities of these given actions being the optimal action. So we get this state, and our policy network now is predicting a probability distribution of, we can basically aggregate them into our policy. So we can say our policy is now defined by this probability distribution. And now to compute the action that we should take, we simply sample from this distribution to predict the action that we should execute. In this case, it's the car going left, which is A1. But since this is a probability distribution, the next time we sample, we might get to stay in the same place. We might sample action 2, for example, because this does have a non-zero probability, a probability of 0.1. Now note that because this is a probability distribution, this P of actions given our state must sum to 1. Now, what are some of the advantages of this type of formulation over, first of all, over Q learning like we saw before? Besides the fact that it's just a much more direct way to get what we want. Instead of optimizing a Q function and then using the Q function to create our policy, now we're going to directly optimize the policy. Beyond that, though, there is one very important advantage of this formulation, and that is that it can handle continuous action spaces. So this was an example of a discrete action space, what we've been working with so far in this Atari breakout game. Moving left, moving right, or staying in the center. There are 3 actions, and they're discrete. There's a finite number of actions here that can be taken. For example, this is showing our action space here is representing the direction that I should move. But instead, a continuous action space would tell us not just the direction, but how fast, for example, as a real number that I should move. Questions like that are infinite in their number of possible answers. This could be 1 meter per second to the left, half a meter per second to the left, or any numeric velocity. It also tells us direction by nature through plus or minus sign. So if I say minus 1 meter per second, it tells me that I want to move to the left at 1 meter per second. If I say positive 1, it tells me I want to move to the right at 1 meter per second. But now, when we plot this as a probability distribution, we can also visualize this as a continuous action space. And simply, we can visualize this using something like a Gaussian distribution in this case, but it could take many different. You can choose the type of distribution that fits best with your problem set. Gaussian is a popular choice here because of its simplicity. So here again, we can see that the probability of moving to the left, faster to the left, is much greater than moving faster to the right. And we can actually see that the mean of this distribution, the average, the point where this normal distribution is highest, tells us an exact numerical value of how fast it should be moving. Not just that it should be moving to the left, but how fast it should be moving to the left. Now, let's take a look at how we can actually model these continuous action spaces with a policy gradient method. Instead of predicting the probability of taking an action given a possible state, which in this case, since we're in the continuous domain, there would be an infinite number of actions, let's assume that our output distribution is actually a normal Gaussian and output a mean and a variance for that Gaussian. Then we only have two outputs, but it allows us to describe this probability distribution over the entire continuous space, which otherwise would have been infinite, an infinite number of outputs. So in this case, that's if we predict that the mean action that we should take, mu, is -1 and the variance is of 0.5, we can see that this probability distribution looks like this on the bottom left-hand side. It should move to the left with an average speed of -1 meters per second and with some variance. So it's not totally confident that that's the best speed at which it should move to the left, but it's pretty set on that being the place to move to the left. So for this picture, we can see that the paddle needs to move to the left if we actually plot this distribution like this, and we can actually see that the mass of the distribution does lie on the left-hand side of the number line. And if we sample, for example, from this distribution, we can actually see that in this case, we're getting that the action that we should take, the concrete velocity that should be executed, would indicate that we need to move left, negative, at a speed of 0.8 meters per second. So again, that means that we're moving left with a speed of 0.8 meters per second. Note here that even though the mean of this distribution is -1, we're not constrained to that exact number. This is a continuous probability distribution. So here we sampled an action that was not exactly the mean, but that's totally fine. And that really highlights the difference here between the discrete action space and the continuous action space. This opens up a ton of possibilities for applications where we do model infinite numbers of actions. And again, like before, like the discrete action case, this probability distribution still has all of the nice properties of probability distributions, namely that the integral of this computed probability distribution does still sum to 1. So we can indeed sample from it, which is a very nice confirmation property. Okay, great. So let's take a look now of how the policy gradients algorithm works in a concrete example. Let's start by revisiting this whole learning loop of reinforcement learning again that we saw in the very beginning of this lecture. And let's think of how we can use the policy gradient algorithm that we have introduced to actually train an autonomous vehicle using this trial and error policy gradient method. So with this case study of autonomous vehicles or self-driving cars, what are all of these components? So the agent would be our vehicle. It's traveling in the environment, which is the world, the lane that it's traveling in. It has some state that is obtained through camera data, LiDAR data, radar data, etc. It makes actions. What are the actions that it can take? The actions in this case are the steering wheel angle. Again, this is a concrete example of a continuous action space. You don't discretize your steering wheel angle into unique bins. Your steering wheel angle is infinite in the number of possibilities it can take, and it can take any real number between some bounds. So that is a continuous variable that we're trying to model through this action. And finally, it receives rewards in the form of the distance it can travel before it needs some form of human intervention. So let's now dive in, now that we've identified all of those. So how can we train this car using policy gradient network in this context? Here we're taking self-driving cars as an example, but you can hopefully see that we're only using this because it's nice and intuitive, but this will also apply to really any domain where you can identify and set up the problem like we've set up the problem so far. So let's start by initializing our agent. Again, our agent is the vehicle. We can place it onto the road in the center of the road. The next step would be to let the agent run. In the beginning, it doesn't run very well because it crashes and, it's never been trained before, so we don't expect it to run very well. But that's okay, because this is reinforcement learning. So we run that policy until it terminates. In this case, we mark terminations by the time that it crashes. It needs to be taken over. Along that, what we call rollout, we start to record all of the state action pairs, state action reward pairs. So at each step, we're going to record where was the robot, what was its state, what was the action that it executed, and what was the reward that it obtained by executing that action in that state. Now, next step would be to take all of those state action reward pairs and actually decrease the probability of taking any action that it took close to the time where the termination happened. So close to the time where the crash occurred, we want to decrease the probability of making any of those actions again in the future. Likewise, we want to increase the probability of making any actions in the beginning of this episode. Note here that we don't necessarily know that there was something good in this first part of the episode. We're just assuming that because the crash occurred in the second part of the episode, that was likely due to an action that occurred in that second part. This is a very unintelligent, if you could say, algorithm, because that's all it assumes. It just tries to decrease the probability of anything that resulted in a low reward and increase the probability of anything that resulted in a high reward. It doesn't know that any of these actions were better than the other, especially in the beginning, because it doesn't have that kind of feedback. This is just saying that we want to decrease anything that may have been bad and increase anything that would have been good. And if we do this again, we can see that the next time the car runs, it runs for a bit longer. And if we do it again, we do the same thing. Now, on this rollout, we decrease the probability of actions that resulted in low reward and increase the probability that resulted in positive or high reward. We reinitialize this and we run it until completion and update the policy again. And it seems to run a bit longer, and we can do this again. And we keep doing this until eventually it learns to start to follow the lanes without crashing. And this is really awesome, I think, because we never taught this vehicle we never taught it anything about lanes. We never taught it what a lane marker is. It learns to avoid lanes, though, and not crash just by observing very sparse rewards of crashing. So it observed a lot of crashes, and it learned to say, like, okay, I'm not going to do any of these actions that occurred very close to my crashes. And just by observing those things, it was able to successfully avoid lanes and survive in this environment longer and longer times. Now, the remaining question is how we can actually update our policy on every training iteration to decrease the probability of bad events and increase the probability of these good events, or these good actions, let's call them. So that really focuses and narrows us into points 4 and 5 in this training algorithm. How can we do this learning process of decreasing these probabilities when it's bad and increasing the probabilities when they're good? Let's take a look at that in a bit more detail. So let's look at specifically the loss function for training policy gradients, and then we'll dissect it to understand exactly why this works. So this loss consists of really two parts that I'd like to dive into. The first term is this log likelihood term. The log likelihood of our policy, our probability of an action given our state. The second term is where we multiply this negative log likelihood by the total discounted reward, or the total discounted return, R of t. So let's assume that we get a lot of reward for an action that had very high log likelihood. This loss will be great, and it will reinforce these actions because they resulted in very good returns. On the other hand, if the reward is very low for an action that it had high probability for, it will adjust those probabilities such that that action should not be sampled again in the future because it did not result in a desirable return. So when we plug in this loss to the gradient descent algorithm to train our neural network, we can actually see that the policy gradient term here, which is highlighted in blue, which is where this algorithm gets its name. It's the policy, because it has to compute this gradient over the policy part of this function. And again, just to reiterate once more, this policy gradient term consists of these two parts. One is the likelihood of an action, and the second is the reward. If the action is very positive, very good, resulting in good reward, it's going to amplify that through this gradient term. if the action is very probable, or sorry, not very probable, but it did result in a good reward, it will actually amplify it even further. So something that was not probable before will become probable because it resulted in a good return. And vice versa on the other side as well. Now, I want to talk a little bit about how we can extend some of these reinforcement learning algorithms into real life. And this is a particularly challenging question because this is something that has a particular interest to the reinforcement learning field right now, and especially right now, because applying these algorithms in the real world is something that's very difficult for one reason, or one main reason, and that is this step right here. Running a policy until termination. That's one thing that I touched on, but I didn't spend too much time really dissecting it. Why is this difficult? Well, in the real world, terminating means, well, crashing, dying, usually pretty bad things. And we can get around these types of things usually by training in simulation. But then the problem is that modern simulators do not accurately depict the real world. And furthermore, they don't transfer to the real world when you deploy them. So if you train something in simulation, it will work in simulation. It will work very well in simulation. But when you want to then take that policy, deploy it into the real world, it does not work very well. Now, one really cool result that we created in my lab was actually developing a brand new photorealistic simulation engine specifically for self-driving cars that I want to share with you that's entirely data-driven and enables these types of reinforcement learning advances in the real world. So one really cool result that we created was developing this type of simulation engine here called VISTA, and allows us to use real data of the world to simulate brand new virtual agents inside of the simulation. Now, the results here are incredibly photorealistic, as you can see, and it allows us to train agents using reinforcement learning in simulation, using exactly the methods that we saw today, so that they can be directly deployed without any transfer learning or domain adaptation directly into the real world. Now, in fact, we did exactly this. We placed agents inside of our simulator, trained them using exactly the same policy gradient algorithm that we learned about in this lecture. And all of the training was done in our simulator. Then we took these policies and put them directly in our full-scale autonomous vehicle, as you can see in this video. And on the left-hand side, you can actually see me sitting in this vehicle on the bottom of the interior shot. You can see me sitting inside this vehicle as it travels through the real world, completely autonomous. This represented the first time, at the time of when we published these results, the first time an autonomous vehicle was trained using RL entirely in simulation and was able to be deployed in the real life. A really awesome result. So now we have covered the fundamentals behind value learning, as well as policy gradient reinforcement learning approaches. I think now it's really important to touch on some of the really remarkable deep reinforcement learning applications that we've seen in recent years. And for that, we're going to turn first to the game of Go, where reinforcement learning agents were put to the test against human champions and achieved what at the time was, and still is, extremely exciting results. So first, I want to provide a bit of an introduction to the game of Go. This is a game that consists of 19 by 19 grids. It's played between two players who hold either white pieces or black pieces, and the objective of this game is to occupy more board territory with your pieces than your opponent. Now, even though the grid and the rules of the game are very simple, the problem of Go, solving the game of Go, and doing it to beat the grandmasters is an extremely complex problem. It's actually because the number of possible board positions, the number of states that you can encounter in the game of Go is massive. With the full-size board, there are a greater number of legal board positions than there are atoms in the universe. Now, the objective here is to train an AI, to train a machine learning or deep learning algorithm that can master the game of Go, not only to beat the existing gold standard software, but also to beat the current world human champions. Now, in 2016, Google DeepMind rose to this challenge, and several years ago, they actually developed a reinforcement learning-based pipeline that defeated champion Go players. And the idea at its core is very simple and follows along with everything that we've learned in this lecture today. So first, a neural network was trained, and it got to watch a lot of human expert Go players, and it basically learned to imitate their behaviors. This part was not using reinforcement learning. This was using supervised learning. You basically got to study a lot of human experts. Then they used these pre-trained networks to play against reinforcement learning policy networks, which allows the policy to go beyond what the human experts did and actually play against themselves and achieve actually superhuman performance. In addition to this, one of the really tricks that brought this to be possible was the usage of this auxiliary network, which took the input of the state of the board as input and predicted how good of a state this was. Now, given that this network, the AI could then hallucinate, essentially, different board position actions that it could take and evaluate how good these actions would be given these predicted values. This essentially allowed it to traverse and plan its way through different possible actions that it could take based on where it could end up in the future. Finally, a recently published extension of these approaches just a few years ago, in 2018, called AlphaZero, only used self-play and generalized to 3 famous board games. Not just Go, but also chess, shogi, and Go. And in these examples, the authors demonstrate that it was actually not necessary to pre-train these networks from human experts, but instead they optimized them entirely from scratch. So now this is a purely reinforcement learning based solution, but it was still able to not only beat the humans, but it also beat the previous networks that were pre-trained with human data. Now, as recently as only last month, very recently, the next breakthrough in this line of works was released with what is called MuZero, where the algorithm now learned to master these environments without even knowing the rules. I think the best way to describe MuZero is to compare and contrast its abilities with those previous advancements that we've already discussed already today. So we started this discussion with AlphaGo. Now, this demonstrated superhuman performance with Go using self-play and pre-training these models using human grandmaster data. Then came AlphaGo Zero, which showed us that even better performance could be achieved entirely on its own, without pre-training from the human grandmasters, but instead directly learning from scratch. Then came AlphaZero, which extended this idea even further beyond the game of Go and also into chess and shogi, but still required the model to know the rule and be given the rules of the games in order to learn from them. Now, last month, the authors demonstrated superhuman performance on over 50 games, all without the algorithm knowing the rules beforehand. It had to learn them as well as actually learning how to play the game optimally during its training process. Now, this is critical because in many scenarios, we do not know the rules beforehand to tell the model. When we are placed in the environment, sometimes the rules are unknown. The rules or the dynamics are unknown. Objects may interact stochastically or unpredictably. We may also be in an environment where the rules are simply just too complicated to be described by humans. So this idea of learning the rules of the game or of the task is a very, very powerful concept. And let's actually walk through very, very briefly how this works, because it's such an awesome algorithm. But again, at its core, it really builds on everything that we've learned today. So you should be able to understand each part of this algorithm. We start by observing the board state. And from this point, we predict or we perform a tree search through the different possible scenarios that can arise. So we take some actions and we look at the next possible scenarios or the next possible states that can arise. But now, since we don't know the rules, the network is forced to learn the dynamics model of how to do this search. So to learn what could be the next states given the state that it currently sees itself in and the action that it takes. Now, at the base time, this gives us this probability of executing each of these possible actions based on the value that it can attain through this branch of the tree. And it uses this to plan the next action that it should take. This is essentially the policy network that we've been learning about, but amplified to also encounter this tree search algorithm for planning into the future. Now, given this policy network, it takes this action and receives a new observation from the game and repeats this process over and over again. until, of course, that the game finishes or the game is over. This is very, very similar to how we saw AlphaZero worked. But now the key difference is that the dynamics model, as part of the tree search that we can see at each of these steps, is entirely learned and greatly opens up the possibilities for these techniques to be applied outside of rigid game scenarios. So in these scenarios, we do know the rules of the games very well, so we could use them to train our algorithms better. But in many scenarios, this type of advancement allows us to apply these algorithms to areas where we simply don't know the rules and where we need to learn the rules in order to play the game. Or simply where the rules are much harder to define, which in reality, in the real world, many of the interesting scenarios, this would be exactly the case. So let's briefly recap with what we've learned in the lecture today. We started with the foundations of deep reinforcement learning. We defined what agents are, what actions are, what environments are, and how they all interact with each other in this reinforcement learning loop. Then we started by looking at a broad class of Q learning problems, and specifically the deep Q network, where we try to learn a Q function given a state and action pair, and then determine a policy by selecting the action that maximizes that Q function. And finally, we learned how we could optimize, instead of optimizing the Q value or the Q function, learn to directly optimize the policy straight from the state. And we saw that this has really impactful applications in continuous action spaces where Q functions or this Q learning technique is somewhat limited. So thank you for attending this lecture on deep reinforcement learning. At this point, we'll now be taking the next part of the class, which will be focused on reinforcement learning, and you'll get some experience on how you can apply these algorithms onto all by yourself, specifically focusing on the policy gradient algorithms in the context of a very simple example of Pong, as well as more complex examples as well. So you'll actually build up this body and the brain of the agent and the environment from scratch, and you'll really get to put together a lot of the ideas that we've seen today in this lecture. So please come to the Gather Town if you have any questions, and we'd be happy to discuss questions on the software lab specifically, as well as any questions on today's lecture. So we look forward to seeing you there. Thank you.